This is the second lecture of Chapter 5, which deals with gases, liquids, and solids. Before we start, however, let us review what we did in the last lecture, or what we covered. We looked at pressure and measurements of pressure. We also looked at different gas laws, the Boyle's law, the Charles's law, and the Gay-Lussac's law. It was possible, we discovered, to combine these laws to get the combined gas law, which is written here. We also looked at Avogadro's law, and from that we derived the ideal gas law, and here is the equation. So don't forget, these equations you should know, well, you should know them, they will be given to you. You should know how to use them to solve any of the unknowns. We also looked at partial pressure, Dalton's law of partial pressures. And we looked at the kinetic theory, which is really a description of the movement of molecules in a gas. For today's lecture, we will look at the different states of matter, and in particular, we'll look at the intermolecular forces between molecules. We'll also look at liquids and the properties of liquids. And then lastly, we'll look at solids and phase changes, which means going from a solid to a liquid or from a liquid to the gaseous state. Okay, let's get started by first defining and looking at intermolecular forces. As the name suggests, inter means across. So it involves molecules and the attraction between molecules, as you can see here. These attractions exist in the gaseous phase, the liquid phase, and the solid phase. So it's important to know what these intermolecular forces are and how strong they are on a relative scale. So let's just imagine a gas here at standard temperature and pressure. You may recall that standard temperature and pressure is 0 K and the pressure is 1 atmosphere. The gas molecules are moving relatively slowly. But if you should increase the temperature or change the pressure, then the movements differ, and basically in terms of the intermolecular attraction between any two molecules. So what we'll do here is let's define the intermolecular attractions and look at the type. We mentioned intermolecular attractions are the attractions that exist between two molecules, or molecules in general. The different types that we'll discuss here are three. One's called the London Dispersion Forces. In some books you'll see it as the Van der Waals attractions. Next we look at the dipole-dipole attractions. And lastly we'll look at the hydrogen bonding, or hydrogen bonds. So let us start by looking at the London Dispersion Forces, or the Van der Waals. In a molecule, in an atom such as this, let's start with the atom. In an atom such as this, which has electrons, if it's large, we say it's polarizable. It's possible for the electrons to be at one end of the molecule compared to being at the other end. If, for example, the electrons were mostly on this side here that I'm highlighting in red, you can see there's a partial negative charge on that end. Partial negative because most of the electrons are over in this region. It in turn induces a partial positive opposite charge in another molecule. So the electrons would be over on this end here for the other molecule, and this end would be partially positive. Because opposites attract here, there's an attraction between these two atoms. And we call that the London dispersion force. Here's another example. If you have a molecule in this case, where, let's look at this molecule, carbon, 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 bonded to hydrogen, pretty large. It's possible for the electrons to be on one region of that molecule. So it acquires a partial negative charge, partial, and it induces a partial positive charge in another molecule because opposite charges attract each other. There'll be an attraction between these two molecules, and that's called the London dispersion forces. Okay, so London dispersion forces are very weak. This gives you a brief summary. They're very weak, about 0.1 to 2 kilocalories per mole. So the main thing here is they're relatively weak. And in general, London dispersion forces increases as the mass and number of electrons of a molecule increases. So a large molecule, as you'd expect, would have stronger London forces compared to a smaller molecule that exists. So as we can, the next one that we look at here is the dipole-dipole interactions. So this is another type of intermolecular attraction. The first is the London. The next here is the dipole-dipole attraction. If you look at acetone, this molecule is acetone. You can see here, or this is the Lewis dot structure of acetone. You can see here this bond is in fact a polar covalent bond. You may recall we discussed polar covalent bonds in the previous chapters. Why is it called a polar covalent bond? Because carbon here is bonded to oxygen, which is electronegative or more electronegative than carbon. So look at your periodic table. You'll see that oxygen is to the right of carbon. Therefore, the electrons in this bond, this double bond here, are closer to the oxygen because it's more electronegative. And remember, electronegativity here means the tendency of an atom to pull electrons towards itself. So the oxygen atom here in this molecule will pull these covalent bonds, these covalent electrons, closer to itself than carbon. Hence, there's a partial negative on oxygen and in turn a partial positive on carbon. Two poles. That's why it's called a dipole. If there's another molecule of acetone as shown here, here's a partial negative, here's a partial positive, and of course, as you'd expect, there would be an attraction. This type of attraction is different from the London forces. This type of attraction is called the dipole-dipole attraction. It's much stronger than the London forces. And so, summary, acetone being a polar molecule, key here is a polar molecule, we have dipole-dipole interaction. For the previous molecule, previous attraction, those molecules were non-polar. This gives us a summary here. So let us look at this molecule, butane, non-polar. So the type intermolecular attraction that you'll find here is London forces. Here is acetone, which is a polar molecule, as you can see from the polar covalent bond. the type of attraction that exists there would be dipole-dipole attraction. Let us look at the third intermolecular attraction, and that is the hydrogen bonds. Let's define it first and then we'll apply it. So hydrogen bond is the attraction between a partial positive charge of a hydrogen that's bonded to an electronegative atom. So let's look at water here. Oxygen is a lot more electronegative than hydrogen. As a matter of fact, looking at your periodic table, hydrogen is the least electronegative atom. So therefore, oxygen is a lot more electronegative than hydrogen. So the electrons in these bonds here, these two bonds here, are closer to the oxygen than to the hydrogen. So therefore, this acquires a partial negative charge, as shown here. The hydrogen will, of course, acquire a partial positive charge, as shown here. So what you can expect is if there's a partial negative and a partial positive, there is an attraction here, and that's called a hydrogen bond. So this is really a dipole-dipole attraction, but a specific one because it involves hydrogen. Because hydrogen is the most electropositive or least electronegative atom, this is a special type of bond and it's called hydrogen bonding, and it is much stronger than the dipole-dipole or the London dispersion forces. So this will be your strongest intermolecular attraction. So this gives a summary. So here we have our hydrogen bonding. Notice it's about 2 to 10 kilocalories per mole. And our London forces are in the region of 1 kilocalories per mole. So therefore, the hydrogen bonding is a very strong intermolecular attraction, keeping two molecules together compared to London forces or dipole-dipole interactions. So let us see how we can apply all of this knowledge here, and we'll look at evaporation and condensation. So first of all, let us define evaporation. So molecules in a liquid are constantly moving. And of course, at some point, as you know, you put a pot of water on the stove. At some point, you supply heat to it. You get the molecules going from the liquid phase into the gaseous phase. That's, of course, called evaporation. So once again, we're looking at evaporation as moving molecules from the liquid phase into the gaseous phase, but we'll have to supply energy to do that. This gives you a graphical illustration. So let us look here at molecules in the vapor phase. Here they are. And in the liquid phase here, you'd expect these molecules here to be attracted to each other because of intermolecular attractions. If we supply enough heat to this liquid, it will have to break these intermolecular attraction to give us the individual molecules in the gaseous phase. Okay, let's see why that is so important. So the boiling point of compounds depend on two factors, primarily two factors. The first is the nature and strength of intermolecular forces, the strength of intermolecular forces. And the other has to do with the weight, the size and weight of the molecules. So if there are very strong intermolecular force, a liquid is harder to boil, more energy is needed, we need a higher, it has a higher boiling point. A molecule that has a very heavy molecular weight requires a lot of energy to get the molecule into the vapor phase. Therefore, these type molecules typically have higher boiling points. Let's look at this table down here. So chloroform, which has a molecular weight of 120, has a boiling point of 62. On a relative scale, however, water, which has, as you can see here, has a molecular weight of 18, has a boiling point of 100 degrees. It's much higher. So the question now is, why is it that chloroform, which has a molecular weight a lot larger than water, has a boiling point much lower than that of water? Because we would expect that a lot more energy is needed to vaporize chloroform compared to water based on its molecular mass. But we're seeing the opposite here. As scientists and as chemists, we need to apply the concepts that we have just learned and see if we can explain what's happening here. Let's see if we can explain that. And the explanation lies in hydrogen bonding. For water, there's a very strong hydrogen bond because of the partial positive on hydrogen and the partial negative on oxygen, creating a very strong hydrogen bond here. Chloroform, as you saw in the previous structure, does not have a hydrogen bonded to an electronegative atom. So you may want to take out your periodic table and draw the structure of chloroform, and you will notice that a hydrogen is not bonded to an electronegative atom. All the hydrogens are bonded to carbon. So that explains why water has such a high boiling point, because of the strong intermolecular hydrogen bonding that exists. Let us look at another concept and try to apply some of the knowledge that we've learned here. So cooling a liquid results in the less movement of the molecules, or the attraction becomes much stronger and they become much closer. So the molecules in a liquid are attracted to each other much tightly based on these intermolecular attraction. So what we say is we can crystallize a liquid or solidify a liquid, which means taking a liquid into its solid form. So the formation of a solid from a liquid is crystallization or solidification. An example is liquid water going to ice. Here is solid carbon dioxide. Of course, as you know, solid carbon dioxide is dry ice. And of course, carbon dioxide is a gas. So once you liquefy that, once you take it directly to the solid phase, it becomes dry ice. This carbon dioxide is unique. It does not liquefy, it goes directly from carbon dioxide gas into the solid phase. Okay, let us apply some of this knowledge here. We're looking at phase changes. So we're going to change phases from a liquid to a solid and from a liquid to a gas. You may remember the definition of a phase is any part of a matter that's uniform throughout, homogeneous. So an example here is the three phases of water. We have the solid phase, of course you know that as ice. We have the liquid phase, that's water, and that we typically describe as just water. And we have the gaseous phase, we describe that as steam. So those are the three phases of water. What we'll do in the next few slides here is we'll apply that concept to solving different problems in this phase change or phase changes here. So a phase change is going from one physical state into another. So we can go from the gaseous phase to the liquid, or the liquid to the gas, or the liquid to the solid, or solid to liquid. So the application that we look at here is mostly involving water. First, let us set this up so you can imagine what's going on. So remember, we said as chemists and scientists, we are very good at visualizing what we're studying. Even though sometimes we cannot get in the lab to physically see it, but we sit around our desk and visualize what we're analyzing so we can apply some of these concepts to understand it. So imagine a glass of water, which I've shown here. So this glass of water contains ice. So it contains ice and water. Of course, as you know, ice, the temperature of ice is 0 degrees Celsius. If you should put a thermometer in here, it will show 0 degrees Celsius. It's at room temperature. So let's take it out and put it at room temperature on the counter in the kitchen. So that means that at room temperature, heat is being supplied from the room. After a while, what you'll notice is that all the ice melts and we just have a glass of water. But the process involves that ice is melted because of the heat that's transferred from the environment. But the key here is that the temperature remains 0 until all the ice melts. So even though we are supplying heat to this ice to melt it, the temperature in this glass of water here is still 0. So the question now becomes, the heat that's supplied to the glass of water, where is it going? Because it is not increasing the temperature until, of course, all the ice melts. Let's see where this heat is going. There is a term here that will introduce, the heat of fusion. And the heat of fusion is the heat required to separate or to break these intermolecular forces that exist between molecules of water. The heat of fusion for ice is 80 calories per gram. So it's a physical property. It's measurable. It's in books. It's in tables. So you need not memorize this. It is a value that's readily available. So the heat of fusion, the heat required to melt a gram of ice is 80 calories. So the heat that's supplied goes to melt the ice and not raise the temperature. So here's a question. How much heat is required to melt 1 gram of ice at 0 degrees? Conversion equation here, remember, 1 is always given. Conversion equation. Your job is just to utilize that to solve a problem. So we know that the heat is equal to the mass times the heat of fusion, which of course is a constant. So that's always given. So if you're calculating for the heat, it's just a matter of substituting these values into this equation and solve it, and you get 80 calories. So it takes 80 calories to melt 1 gram of ice. So notice it's not going to increase the temperature, but just to melt 1 gram of ice, which means taking the molecules further apart by breaking the intermolecular attractions. For water and ice, it's basically hydrogen bonding. Let us look at another example here. So let's get outside the box of water. Of course, as you know, we can melt iron, for example. The heat of fusion for iron is 63 3.7 calories per gram. So if you ask how much heat is required to melt 50 grams of iron, notice here 50 grams this time, here's the conversion equation that you'll need and will be given. This is a constant, so that will be given or known. So we just have to supply the integrate or incorporate these numbers with appropriate units into this equation. We have 50 grams right here, and the heat of fusion, this time it's the heat of fusion for iron, because that's what we are calculating, not ice. So look at your table. In the book, you will see the heat of fusions for different molecules, different compounds. Substitute that value here, do the multiplication, and you end up with 3.2 times 10 to the third calories, or 3.2 kilocalories. So, conclusion, if you have 50 grams of 50 grams of iron, 50 grams of iron, it will take 3.2 kilocalories to melt that 50 grams of iron, of course, at the melting point of iron. Notice it's at the melting point of iron. Let's look at another phase transfer. This time it's boiling. So consider a pot of water boiling on the stove, as we can see here. The temperature is 100 degrees. We know that because water boils at 100 degrees. It will remain 100 degrees C until all the water evaporates. So if you put a pot of water on the stove and turn it on, the heat goes in to increase the temperature to 100 degrees. Once it gets to 100 degrees, evaporation occurs. The heat is still being supplied, but it's not going to raise the temperature of the water. So the temperature of the water here is always 100 degrees C, but we're supplying heat. So the question now becomes, where is the heat going? As you can imagine, the heat is going to break up the intermolecular attraction that exists between two molecules in the liquid phase. We're going to break this up and take this into the gaseous phase. So that's where the heat is going, to break this up. We know from water they're very strong intermolecular attraction. It's specifically hydrogen bonding. So let's apply that concept to solving some problems. The heat of vaporization, of course, notice the term now. It's heat of vaporization, not fusion. Heat of vaporization for water, specific for water, is 540 calories per gram. So it's a lot of heat that's required to take liquid water into steam. This is a constant for water. It varies for different compounds, but for water it's 540 calories per gram. So the question now becomes, how can we apply this? How much heat is required to vaporize 1 gram, pardon me, this should be 1 gram of water at 100 degrees C? The conversion equation is right here. As you can imagine, heat is equal to the mass times heat of vaporization. This is a constant that's given for a particular compound. So it will be given. Your job as a chemist here is just to recognize this conversion equation, which will be given, and utilize that conversion equation to solve the problem to determine heat. Plug the numbers in. 1 gram, as given here. Now we have 540 calories per gram. That's the heat of vaporization for water. And of course, as you can see here, it's 540 calories. So it takes lots of heat to break the intermolecular attraction in liquid water to convert it to steam. That's why they say, that's why it's known that steam burns you much more than hot water, because of the heat that's involved, that's acquired in vaporization of the liquid water. Let's apply this to another example. How much heat is required to vaporize 83.3 grams of water? The conversion equation that will be given, or you should know exists, is right here. Heat is equal to mass times heat of vaporization. Very simple equation. There's two variables. So the heat here that you need to calculate, because it said how much heat, is the mass is 83 grams, as you can see here. Notice I'm including my units because they will cancel. And the heat of vaporization is 540 calories per gram. That's a constant, will be given. Plug these numbers into your calculator, and what you have over here is 4.5 times 10 to the 5th, or 45 kilocalories. So let's apply this here to this example. Heat of vaporization of water again is, notice that's a constant, so that's always will be given. What mass of water at 100 degrees C, because that's the boiling point of water, will be vaporized given 45 kcals per mole? So given 45 kcals per mole, how much water can be vaporized? So again, what we're asking is, did you understand this equation? Do you know how to utilize that equation? So that will be given. So now we have the heat, which is right here. We do not have the mass. We need to calculate the mass. But we do have the heat of vaporization, which is 540. So you plug that in, and what you'll get over here is 83.3 grams. So once again, for the quiz and for the exam, make sure that you know how to utilize this conversion equation to calculate any one of these unknowns. Calculate the heat, you should be able to calculate the heat, you should be able to calculate the mass. Of course, you won't be asked to calculate the heat of vaporization because that is a constant. Okay, let's look here at another example here, and that's called specific heat. So again, let us imagine here you have a gram of water. So this is liquid water, and you're supplying heat to it to raise the temperature. So in other words, you have liquid water. Just imagine again, you have a glass of water, and it is at 0 degrees C. It's already melted. All the ice have already melted, and you want to take that to 100 degrees C before it starts boiling. So once again, let's set this up again. You have a pot of water. Let's use a pot of water on the stove. It's at 0 degrees C because it had some ice in it. All the ice has now been melted. So the temperature is 0 degrees C. And we turn on the stove. We need to get it to 100 degrees C before it starts to boil. How much heat is needed? You know, heat is needed because the temperature changes from 0 degrees C to 100 degrees C. How much heat is needed? What you need is a conversion equation. Here's a conversion equation. Heat is equal to mass times specific heat. Specific heat is a constant, as you saw in the previous chapter, times the change in temperature. So this equation you've seen before. It's just now applying it to a specific case. We just have to plug these numbers in. So the heat we're trying to calculate here is equal to mass, 1 gram, that's given here, and times specific heat, which is a constant, which is given, so that will be given, times the change in temperature. So T2 minus T1, or T final minus T initial, 100 minus 0, we end up with 100 calories is needed to raise the temperature of water from 0 degrees C to 100 degrees C. That's the end of the chapter 5. So once again, go back and read your chapter and follow along with this video lecture or with the PowerPoints, which I will also post on D2L. And make sure that you have your calculators and your periodic table available, and work the examples in the book, because you will see similar examples on the test and on the quiz. So continue to study hard and get ready for the quiz, which is coming up on Thursday. Okay? Bye.